everyone. Welcome to episode number 649 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by me, Amelia Dalton. This week, my very special guest is imec Scientific Director Axel Nackaerts, and we are talking all about why hardware innovation will be crucial to the future of the AI revolution. We also chat about the biggest challenges for the next generation of AI applications, and how imec is furthering flexibility in hardware innovation for artificial intelligence designs. So, without further ado, please welcome Axel to Fish Fry. Hi, Axel. Thank you so much for joining me.
Hey, good to have me on this show, actually.
Excellent. Okay, so we're talking about next gen AI and the hardware innovation needed to further development in this arena. So, first, Axel, what do you think are the biggest challenges for the next generation of artificial intelligence designs?
The biggest challenge is to figure out what next-gen AI is going to look like. AI is evolving at such a fast pace. The algorithms are changing almost on a daily basis. And doing a good hardware design requires a good knowledge of the algorithm. If you want to be power efficient, fast, you really need to know what you need to calculate. And that is changing rapidly. Last couple of years, we had an evolution from convolutional nets to transformers to variants thereof, and now we're moving into agentic era. And you see a shift in emphasis from learning by training to learning by analysis and retrieving things from, let's say, online sources. And if you design hardware, it's quite different in terms of the type of network traffic, the amount of memory, the type of memory that you would need. It's been a long time that the actual compute was a bottleneck. Now it's remembering things, the types of memory, the memory architecture, and how you stream data through that entire stack to achieve a very efficient result. And I say efficient because, in my opinion, energy efficiency is the most important one. I'm not talking about training. Training is a one-off, and honestly, once we have a good foundation model that can do some reasoning and retrieve things and has learned how to analyze input online and really looking at different documents and providing an answer to the question that is up to date, training becomes less of an issue. So most of the energy is consumed by the inference. And if you look at the energy breakdown there, it's mostly memory transactions. So I believe the secret sauce for next-gen AI is figuring out the best possible type of memory to store all the information that you need to run the AI, and figuring out how to pass information between one node that might be your phone, that might be your desktop, your laptop, that might be the cell tower, somewhere in between, or the data center. So that's a pretty complex set of things to do. And then once you know which technologies to use, you face a choice on how to build your architecture. As an architect, we look at logical entities, things that are one, and then we break them up into the physical implementation of those logical entities. And you have so many choices. You can go for a monolithic design, you can go wafer scale, you can break it down into chiplets, place the chiplets on an electrical interposer, you can go in the future to an optical interposer. There's so many technological choices, and none of them are the solution. You always need to balance the benefits and the costs of each of those solutions to figure out what the best system level solution is. And it's sometimes surprisingly not what you would, as a human, intuitively expect. So maybe we need an AI to come up with the next hardware solution.
I love that. Okay, so how do you think we should go about solving these challenges? It's definitely difficult to predict the next bottleneck or requirement needed for these kinds of designs.
I agree. So first of all, the customer of any hardware system is the software programmer that needs to use it. So listening to how algorithms are evolving and really trying to understand the fundamentals on why a certain AI system is built the way it is from the software standpoint, the actual algorithm that needs to be executed, is extremely important. So once we know that, we figure out the bottlenecks. And if the bottlenecks cannot be solved, let's say in an algorithmic way, we need to figure out something on the hardware side that eliminates it. And it can go very, very deep. It might be that you need to store a lot of data and that the data doesn't need to live very long. You might choose a certain type of memory. And if the memory doesn't exist, we need to figure out a new type of memory or a new way of arranging existing types of memory such that it actually optimally solves the problem. And even so, in the longer run, if AI algorithms continue to evolve as quickly as they do now, it will be hard to kind of pre-bake the hardware to execute those algorithms. So there will come a time that the hardware itself becomes reconfigurable when you're actually executing the AI, whether it's at edge or cloud. And that might require different technologies than the ones that we have today with a different optimization target. It might be that you need a lot more 3D stacked memory, or you need a completely different arrangement of transistors to get to an optimal solution. It's not an easy task, and tracking the changes in the algorithms, because AI is much more than the visible large language models. It's your fridge detecting that something is going wrong inside the fridge. It's you picking up a phone and the phone knowing that it's you. There are many, many different less visible uses of AI that might require different solutions because they have different constraints. So understanding the constraints in which you have to operate, power, mechanical size, size of memory, connectivity, but also the expectations from the user, like how fast should the response come. Sometimes it's, I believe in my use of AI, it would be perfectly fine if the first response of the AI is I have to think a bit about it because I need to retrieve, and it's what RAG systems do today as well. They tell you need to wait a bit. Understanding the algorithms, understanding the constraints, and then having a good view on the technological evolution. Because when we design a system today, we look at the technologies that are available today. So if we want to look at next generation, we have to anticipate on the technologies that will be available in the future. And that's not just a generation after this one. It's further down the road, because if you need to develop a technology, you need 10 years. It's not something that just pops out of a hat. Even if you would use AI to design a technology, it takes a long time to actually get it into production. And that requires quite some guesswork, and it requires building test systems and looking at different possibilities on the architectural side, doing what-if analysis. What if people would make AI that is 100 times larger than today? What if it would be broken down in little pieces? That's the type of work that we do at imec typically, is this, because we're working on semiconductor technology. So we're looking 10, 15 years in the future at least. And that gives us a feel about the different technologies that will be upcoming. And we try to see if we would apply these technologies virtually to solve a design problem today, like designing an accelerator for AI or an entire machine for AI. How would these technological choices impact the architecture, and what would be the impact on the performance and the power? It's not a simple question. It's very much having interdisciplinary teams and an openness of mind that goes beyond the let's just improve the performance of the last generation by 5%, which is something we see a lot when I come from product development in the past myself. And usually the next generation was a minor improvement in terms of performance compared to the previous generation, simply because, well, you couldn't increase costs because technology is expensive, because it takes a lot of time to design. So starting from the standpoint of the future and looking towards today, like I want to be here in 10 years, what is a good road to get here? And I think that looking at every aspect of the problem is the way to go.
Absolutely. So, talk to me a bit more about what imec in particular is doing to further flexibility in hardware innovation for AI applications.
So we are quite deeply rooted in the semiconductor technology. So really the material science, building transistors, building interconnections, optical interconnections and memories. And we have a layer that is specialized in looking at system design, so in the use of those technologies. But everyone working at imec is working with the future in mind. So when you develop a technology, we have technology roadmaps, and those come quite often from the science. We know you can make a transistor a bit smaller, and physics is what it is, chemistry is what it is. So you can only evolve slowly in a certain direction, and you know roughly how much effort it's going to take to get somewhere. So we know this bottom-up evolution of performance of the different components. But very often is the way you structure those, like for instance in memories, you have many, many different possibilities. So we really look at creating new solutions, arrangements in memory, arrangements in materials that nobody has thought about, but that make sense from the standpoint of using those memories, using those materials in making systems more efficient. And whether that's an AI system or not is in fact not that much of a point. AI specifically, the advantage of AI is that we might not know the entire algorithm or the topology of the entire AI system, but AI systems consist of a fairly limited set of functions, the same set of vector additions, the same set of nonlinearities. They're just arranged in a different way. So it kind of allows us to find very specific solutions for those simple operations that will be used. So without knowing how the whole thing will work, you can already work out what the basic building blocks should be. So we prepare that. And then we look at how can we combine these things. Is it going to be on a single chip? Is it going to be on a set of chiplets? And if you need to grow, is it best to have it in separate machines connected with an optical interconnect? Or do you want to have those separate chiplets connected directly to an optical backplane and so on? So we really look at the things that are not done today yet that we think might be feasible from the physics and the device integration standpoint and the system integration standpoint. Do they make sense? And ultimately, we present or kind of de-risk these options for all the companies that are our partners. And our entire ecosystem basically is helped by us kind of trying in advance before it's really in the competition and let's build our own product phase. We de-risk these technologies and we show that they bring a benefit to the entire ecosystem.
I love that. All right, it is time for your off-the-cuff question. So, Axel, if you could have one meal right now, doesn't matter if it's on the other side of the world, you need a passport to get there, what would you have?
Right now, it's pretty hot weather, but it's a bit overcast. I would love to have a catch of the day fish on a beach in Sicily.
I would too. That sounds amazing. Well, Axel, this was super cool. Thank you so much for joining me.
Thanks for having me.
If you would like even more information about this topic, I've included a couple links below the player on this week's Fish Fryin' page on eejournal.com, and of course in the description for this week's YouTube episode as well. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EE Journal. If LinkedIn is more your thing, I dig it. You can follow us or me on LinkedIn, and we are also on Blue Sky Social and Mastodon too. And we have a YouTube channel, youtube.com/EEJournal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series, hosted by me, and our animated series called Libby's Lab. And of course, you can subscribe to our EE Journal YouTube channel as well. Thank you, everyone, for tuning in. If you know of any cool new technology or heck, you just want to chat, shoot me a line at Amelia, that's Amelia, at eejournal.com, or post a comment on our forums on EE Journal. For the week of September 12th, 2025, I'm Amelia Dalton, and you've been fried.